So in that case, they're actually solving the pose problem of what is the location and orientation of the camera by comparing the real-time imagery that you're looking at with the stored historical imagery they have from their Street View project.
Wow.
And that's a case where having a just titanic amount of data on the server side to compare to your real-time observations can give you a very precise location, even if GPS isn't very good.
Welcome to another episode of the Mapscaping Podcast. My name is Daniel, and this is a podcast for the geospatial community. My guest on the show today is Tori Smith. He comes to us from a company called Mapbox, and he is the product manager of Mapbox's computer vision and augmented reality platform. So given that introduction, you might have already guessed that we're going to be talking about computer vision and augmented reality today on the podcast. I really hope you enjoy this episode. I think Tori gives a lot of really interesting insights to augmented reality and also walks us through the basics, what needs to happen in order for this to work. So enjoy the episode. Thanks for tuning in, and I will see you on the other side. Hey Tori, welcome to the podcast. Thank you very much for taking the time to do this with me. Much appreciated, and I'm really looking forward to the conversation. So we're going to be talking about augmented reality and navigation. And obviously that has a big sort of geospatial component. But I'm wondering, before we do that, if you could just take a couple of minutes to introduce yourself to the audience and perhaps how you got involved, with augmented reality and computer vision.
Sure, absolutely. Thanks a lot, Daniel. Thank you for having me. I'm really excited to be here today. So a little about my background. I'm actually a mechanical engineer by training. Grew up on the East Coast and worked a lot on vehicle technologies. Did a couple internships with Ford Motor Company in college, and then decided I want to go a little bit deeper into some of the emerging topics in automotive. And when I came out to California for graduate school, I got exposed to this huge new trend of autonomous vehicles. This was about a decade ago. So after the DARPA challenges that happened, where these teams built self-driving vehicles that could navigate through like obstacle courses in urban or out in the desert, basically, environments, got involved in working on controls and motion planning and things like that. And my first couple jobs after graduate school were actually in building autonomous vehicles. Like the first big project I worked on was basically driving a brand new vehicle off the lot from an Audi dealership and then turning it into a self-driving vehicle over the course of about 8 or 9 months, and then driving that vehicle autonomously from San Francisco to New York. The reason I actually switched more into getting into computer vision was that's like one of the really big tasks of an autonomous vehicle is being able to understand the environment around you, which we often refer to as the perception problem. And when I joined Mapbox was developing a product that was designed to similarly use specifically a camera as a sensor to understand the environment in a driving context. So in a context of moving through the road network and understanding the area around you and figure out how to bring aspects of driving into the frame of reference of what a driver would be seeing rather than looking down at a map. And for the past 3 years, I've been working on various ways of using computer vision and augmented reality together to build some of these new types of experience with a specific focus on navigation and getting from point A to point B.
So oftentimes when I talk to people about computer vision, I mean, a camera is a huge part of it. And here I'm thinking anyway, in terms of augmented reality, the geospatial context is really important. We need to understand the location context of the point of view. Why are cameras and computer vision a good tool for this?
So that's a great question. There's a couple of reasons why cameras are particularly well suited to this task. One of them, especially if we think about working on technologies that are very accessible and widespread in their application and availability, is cameras are everywhere. So if you think about, especially if you're thinking about driving, for example, pretty much every driver in the United States is going to have at least one camera with them, whether it's integrated in the vehicle itself or if it's just on their device that they're carrying with them. Cameras today are on every single laptop pretty much that ships, and they're also included in a lot of IoT devices. So they're quite ubiquitous. The actual hardware to build a camera is we have it down. I guess you'd say we have it down to a science. They're very simple. They're very simple to manufacture. They're not very expensive, and they're in so many different places that really having that innovation connected with sort of the Internet of Things, where it's very simple to have a lot of things that we can do with camera feeds that don't necessarily have to happen right at the camera head. They can happen in the cloud, or it can be a mix of things happening on the edge and the cloud. So the fact that cameras are in so many places and that they're also just recording the visible spectrum of light, which is something very intuitive for humans to work with, means that there's tons of even open source computer vision applications that can do some pretty incredible things with cameras today.
So I completely understand that the argument for that we have cameras all over the place. We have these devices with cameras built in them that have computing power like right beside the camera, and these devices are connected to the internet, so we can make use of cloud computing functions if we need to. I completely understand that argument. But how does a camera help us understand location context?
So it depends a lot on what we're doing. So like one of the tools in the toolbox that you have as someone who's working in this space is a camera feed is very rich information. So you have, in many cases, thousands or millions of, usually it is millions of pixels, and every pixel has a bunch of color information, and it's an enormous problem space. And most of the algorithms that are out there for building, like understanding the environment and then building building augmented reality applications within them, are built on some assumptions that sort of constrain the types of things that you might be encountering. And this is easiest to think about if you imagine a really simple AR application that maybe you just want to make a pizza show up on a dining table. If that's what you're trying to do, then your computer vision application needs to look for things that it thinks are tables, or at the best, like a totally level, flat surface that's either rectangular or square in shape or something like that, and then figure out a surface that I want to render upon. That's pretty straightforward. Like similarly, if you're in a different type of context, if you're driving along the road, one of the tools we use for AR navigation is looking out into the distance. Assuming that we have like a forward-facing camera, we're going to be looking for, okay, can I figure out where the horizon is in this scene? And then can I figure out where the vanishing point is? So where all the straight lines have the same point of intersection at the horizon. If you imagine like looking out into the distance along a long straight highway, like out in the American West or something like that, the left lane markings and the right lane markings will all converge at one point. And if we use that, we can actually use a lot of concepts in basic geometry to understand where each pixel of space is going to correspond to in 3 dimensions. So really in computer vision, what we're looking for are patterns that allow us to assign the pixels of the camera to spaces, or to actual 3-dimensional spaces. And there's sort of that pixel to the world coordinate transformation that we need to do to make any basic AR application work. And cameras are a really powerful tool for doing that.
What do we need to know in terms of location? I feel like we've touched on this just a little bit in the last couple of sentences there. But in terms of location, is it good enough just to have an XY coordinate and then doing our computer vision so we understand where things, where objects sort of disappear off into the horizon? Is that all we need to be able to start building augmented reality applications?
So it does depend a lot on the type of application that you're building. I think because of what I've been working on, I'll focus on applications that are associated with moving around in the world, typically along the road network. And there's actually a couple of different steps that we have to solve. If you want to create something that makes sense and have objects show up in the environment where you're expecting, like a simple example, if you have maybe a parking space you're trying to direct a driver to. There's a couple different types of AR that we can implement. The most simple type is just making an object show up at the side of the road. But if this is something that also needs to be specific to a global coordinate rather than just like, identifying where the curb is very different than identifying exactly where this XYZ coordinate of a curb is on the entire Earth. That requirement is going to depend that you not only understand where objects are relative to the camera, but also having to understand where that camera is relative to the Earth. So that's another reason why cameras are so helpful today, is because so many cameras are attached to devices that also have GPS sensors in them.
So in terms of augmented reality and navigation, we have these cameras, and they're obviously the right tool for the job, as you talked about before. Cameras are, in terms of a cell phone anyway, they're attached to a GPS, they have computing on board, so it sounds like we're ready to go. What are there other sort of things we need to understand in order to calculate the viewpoint? Because I'm thinking the viewpoint of the camera is really important in terms of orientating myself in the real world. Could you talk us through what other kinds of factors we need to calculate?
Sure, that's a great question. So if we think about defining what a camera is in this system, it effectively has 6 degrees of freedom. So the first 3 are pretty straightforward. It's just the X, Y, and Z coordinates. And if we're thinking about where we are in the world, that can also be described with the latitude, the longitude, and then the elevation. And that'll give us a point in space. But if we're talking about a camera, especially if we care about what the camera is pointed at, we also need to define the Euler angles. So the yaw, the pitch, and the roll, which is this full 6 degree of freedom state is referred to as the pose. So we need to know where the camera is, and then from that point, exactly where it's pointed. So as you correctly identified, GPS is huge here because it can give us our latitude, our longitude, and our elevation with pretty good accuracy in most conditions. But then from there, satellites are not going to give us our pose. So figuring out where the camera is pointed from that location relies on some other sensors that we often also have available. So every mobile device that's created today has what's called an IMU in it, an inertial measurement unit, which helps us understand how the phone is pointed because it can measure things like gravity. So that's how your phone, for example, knows whether it should be in portrait mode or landscape mode if you're taking a picture, is because it can sense the direction of gravity. And then if we also have a camera and we're in an outdoor space, then computer vision, or actually even an indoor space, there's a lot of things that computer vision can do to further understand the pose of the camera, specifically the yaw, the pitch, and the roll. And then if we're further thinking about this from a driving context, and we assume that this is a forward-facing camera, we can usually assume that, okay, there's not going to be a lot of roll because the camera is ideally going to be rigidly mounted facing forward. There's not going to be that much pitch unless you're really bouncing up and down a lot. So we really just have to figure out like what is the yaw, which is the z-axis. So the axis that would be like pointed straight up in the air. Like, are we looking a little bit to the left, a little bit to the right, or are we pointed straight forward? So there's a lot of ways that we can constrain and simplify that problem if we think specifically about the driving context. But the sort of minimum viable sensor set to make a lot of these AR applications work, especially in like a driving context, are a camera, a GPS sensor, and a inertial measurement unit, or IMU.
I really appreciate you taking the time to sort of walk us through that. I think it's really important that the listeners of this podcast understand what's involved, like what are the prerequisites, if you will, in order to make this augmented reality and navigation work. And you've done an amazing job of describing that, so thank you very much. Maybe now we could talk about what augmented reality is. Like we've talked about in terms of navigation, and I think a lot of people will sort of have an idea in their head of annotating the real world, so things popping up. Is that what we're talking about here, or is there something more involved?
Sure. I think for a lot of folks that are listening, when they think of augmented reality, they probably very quickly think about some of the games that have been created. So like, I think Pokemon Go is a great example. So augmented reality is basically being able to, there's sort of 2 steps, 2 big steps to think about. Step 1 is, are we able to understand the physical environment around the user to a degree that we can add virtual components to that environment in a way that makes sense? So the really simple example I gave earlier is if you're walking around your house with your camera and you point your camera at a table, can I understand where the table is and make something like a pizza show up on the table? So it's not like in the table, it's not floating above the table, it's actually on the surface of the table. So in that case, step 1 is understand the 3D environment to a certain extent, where I understand like where the main surfaces are, like what are the physical constraints of that environment. And then step 2 is, once I've done that, how do I create objects, which we refer to as rendering? How do we render objects inside of that environment that behave following the basic rules of physics to such an extent that someone looking at that screen or experiencing AR is going to say like, yep, that's a pizza sitting on the table in the same way I would expect it to, or What's really commonly used also in a lot of these applications is like, hey, I want to buy a couch and I want to see if it fits in my apartment, what it'll look like. You can actually have like render a couch in AR in your apartment and say like, yep, it fits, it looks good. I like it. I like how it looks with the rest of the color, the design scheme that I have for this room.
When you're talking about the understanding the real environment here, are we talking about downloading base maps, understanding the 3D structure of the house, or is this something that is calculated on the fly? So this is some software that's built into the device or into the application that recognizes features and objects and understands that they exist in a 3D form.
Yeah, that's a great question. So the answer is actually both. So there's some applications where it doesn't really matter where you are. Like, for example, most tables have the same basic attributes. There is a somewhat flat 2D surface that is suspended several feet above what we identify as the floor in that area. But there's also some applications where it does matter specifically where we are. So if you go back to the Pokemon Go example, in the Pokemon Go application, they actually have a map of the whole world and they create content that corresponds with a lot of public spaces. So for example, if we're in San Francisco, there might be a whole bunch of Pokemon that are in Alamo Square Park or in Golden Gate Park or in the Presidio. And in those examples, we actually care a lot about where the user is roughly in GPS. And we not only want to make the Pokemon show up standing on the ground, but we want to make it show up standing on the ground in this particular area that we know is a great place to encourage congregation.
What would this mean in terms of navigation? So I'm sitting in my car, for example, I'm driving down the road, I've got my augmented reality screen showing me different things. Does that need some kind of base map, some kind of general understanding that, hey, this is the road, and understanding that these are street signs, that objects that aren't moving very much, that are perhaps mapped already? Does it need a base map like that, or can it figure out a lot of the stuff by itself?
That's a great question. So there's a lot of parallels between the types of experiences you can create in AR and the types of requirements that we have in the autonomous vehicle world, which is why it was something that was really interesting for me to work on, coming from in the background of working on autonomous vehicles. So there's two different sort of levels here. So very similarly to the example of having just any table be understood correctly versus understanding a specific point in a park where you want a Pokemon to show up. If you think about this in a driving context, if we're driving down the road, there are tons of computer vision algorithms out there, and many of them are even open source, that can identify, okay, these are the lane markings in the road, because there's a lot of patterns that we can identify. We can also do things like identify all the cars, identify all the pedestrians. So a really simple application would be, okay, every time I see a car, just make a red dot show up above the car in 3D, or every time I see a pedestrian, make a little exclamation point show up above the head of the pedestrian if they're in the road, just to send a warning to the driver. So that works without any location context at all. However, if we're specifically interested in guiding the driver and the real world location and real world destination of that driver are important for what we're building, then we not only need to understand the environment around the driver in a local in a local frame, meaning like just where is the camera relative to what the driver is looking at, but we have two steps to solve. We have to first figure out, as we were talking about earlier, where is the driver relative to the earth, and then where are different components of what the driver is looking at relative to the driver. So an example of that would be, let's say I'm driving across town and I've almost reached my destination, and I want there to be I want to highlight the Starbucks that I'm driving to, and maybe even like show like, oh, if you're going to the drive-through, this is the entrance to that driveway, and have that floating in the environment. So in order for that to work, we need to not only understand the pose of the camera, but we also need to understand the real world coordinates of that point of interest, whether it's the building itself or the entrance to the parking lot or a parking space in the street. So basically, if you imagine looking at a standard map, if you went to any two-dimensional map that you can pan around and look at, even with like satellite imagery overlaid or anything like that, any feature or attribute that you can look at on a 2D map, you can render into the real world in a way that a user can point a camera at it and understand where it is, as long as you know the coordinates of that object. And then really the onus is on us, if we're building an AR application, that we can figure out the pose of the camera in that situation. And if we do that well, then the object will actually show up in AR exactly where the driver, the user, is expecting to see it.
But what about, so placing something on the surface of a building? I'm still struggling with this idea that we just need a location for the object to show up without sort of any understanding of, can I stick it to the side of the building? In which case, which side? Is it visible only from one side of the building, or can I see it all the way through the building? And this can all be done just with one coordinate, and you can figure out, okay, the building is there, that is the surface of the building, I put it on this side of the building, and it's not visible on the other side. Is that correct? The correct way of understanding this?
This is where the type of map that you're dealing with has a lot of bearing. So maybe in a simple example, let's just say, like, I know the rough latitude, longitude coordinates of this building, and it's just a point. So it's like a latitude coordinate, a longitude coordinate, and an elevation coordinate. So if you just have one point, then you could create maybe a big balloon that floats at that location at a certain elevation above the ground. However, if you wanted to create something a little more advanced, then you would actually need more. You would need more map information than that. You would actually need to know the road network. So where is the road relative to that building? And you'd also need to know, assuming this is a building, what is a 3D representation of this building? So the simplest way to represent that would be just understanding, rendering the building as a rectangular prism in the environment is defined by at least probably those 8 different coordinates that define the 8 different corners of that rectangular prism. And then if you understand that, you can actually highlight different faces of that object, assuming you're able to localize that object in the environment. That's where it gets a little more complicated, but the really complex integrations of this involve not only understanding a point coordinate on a map, but actually understanding what physical 3-dimensional space do we expect to be occupied by that point of interest or that building that we're trying to highlight.
Yeah, that makes way more sense to me, that we need to know a certain amount of information about, in this case, the built environment before we can start sticking objects to it and having objects really interact with that built environment in a realistic way. So that makes perfect sense for me. Thank you so much for taking the time to clarify that. I appreciate it. What can we do with AR today? So we've talked a little bit about having balloons pop up, and we've talked about identifying pedestrians and drivers and that kind of thing. Is there any sort of one application out there or one example that you can think of that you think this sort of shows what is possible with this kind of technology? Is there any sort of one flagship example that you would like to highlight for us?
I think the flagship example is sort of the ideal end game that we're trying to get to in building augmented reality experiences focused on drivers. Is if you think about playing video games when you were younger, especially like a Microsoft, like a flight simulator or a combat flight simulator, or even thinking about some of the Star Fox games. But if you imagine if you're flying in an environment, it's sort of the heads up display or HUD for that pilot, that when you look in the environment, you don't just see the naked environment. You actually have a UI that highlights certain things in the environment that you might care about. So for example, if you're flying a mission in Flight Simulator, when you start to get close to the airport where you're supposed to land, or there's another plane in the sky, it'll have a green square around it if it's a friendly. It'll have a red square around it if it is an enemy, and it might even have a couple lines of text saying, "Oh, this is an enemy Spitfire," or this is a friendly Hurricane, or something like that. And this is what's really powerful here, is because it is allowing you to have your eyes on exactly what they would normally be on, but augmenting the environment with more information. And I think the dream state, or the dream end goal here, is to create a similar type of experience that a driver can have in the driver's vehicle. And one of the challenges for creating that is to do a heads-up display. It actually adds a third component to the challenge. So as I was talking about earlier, to do augmented reality navigation, you have to understand where you are. You have to be able to look in the environment and understand where the environment is relative to you. And then the third piece, if you're doing a heads-up display, is the screen is no longer fixed. The screen is projected in between where the driver's eyes are and what the driver is looking at. So in a lot of cases, the application would be this is actually painted onto the windshield. And when you're doing that, you also have to understand where the driver's head is. So you have to track three different things at the same time, which means you also need sensors for all three of those things. And this is quite difficult to do, but we're starting to see early applications of this done pretty well. So I think that's an exciting end state that we're sort of moving toward, where you could have information for the driver that corresponds to what the driver is looking at without the driver having to look down at the cluster or look into the center stack where a screen would be.
You mentioned this before, that there was a huge sort of crossover between autonomous vehicles and augmented reality. When you think about augmented reality today, is it competing with the idea of autonomous vehicles, or is it just part of that evolution? Or are they two completely separate things?
I think there are some ways where they are very related and other ways where they're sort of following parallel paths. So one of the real benefits of autonomous vehicles for the rest of the driver experience is vehicles that have much better sensors on them. Like if you look at what types of sensors were on vehicles 25 years ago, like when I was a little kid, you like wouldn't even have GPS in the car in most cases, unless it was like a very advanced vehicle. And then if you look at cars today, I think about the car I drive today, it has a couple of cameras. It has a backup camera. It has a forward-facing camera with some computer vision built into it. It has a radar sensor that can actually look ahead and is really good for identifying other vehicles in the environment. It has quite advanced sensors on board for understanding the speed of my vehicle as I'm driving. It has a quite good GPS. So all these sensors together makes it very good at solving both of those first two problems I was talking about. So understanding where is the vehicle and where are other objects in the environment relative to the vehicle. And even though in the case of my vehicle, there's no AR in it, these features are all designed for safety, whether it's to understand like, hey, I'm drifting out of my lane, or I'm getting too close to the vehicle in front of me, or there is a pedestrian right behind my car and I'm backing out of my parking space. The same sensors that are helpful for situational awareness for driver safety, you sort of get for free, in that case, information about how we would want to draw the environment with AR. And in some cases, the AR component actually comes in as part of the safety system. So if you imagine, I think there's some BMW and Mercedes vehicles out today, for example, when you're backing up, the ultrasonic sensors can see things that are out of the driver's field of view and will actually render like big rectangles that show the extent of like, hey, there's a log here, or there is the wall is right here, and it will actually show you very clearly when you're backing up. And that's actually using AR as an augmentation for safety. And even if the vehicle is driving itself, if we look farther out into the future, there's a lot of cases where augmented reality can still be helpful textual information for the driver, whether it's showing you like, hey, the car is coming to a stop and I just highlighted the building you're supposed to walk into to drop off this package, or if it's a self-driving taxi, like this is the entrance point for the restaurant that you're going to. There's a lot of ways that this actually plays together very harmoniously.
Up until now, we've been talking about augmented reality as a way of annotating the world. I'd just like to run an idea past you here, and I'd be really interested to hear what you think. So a wee while ago, I saw it was a Kickstarter project, and it was this pair of glasses. You could put these glasses on, and it would remove any screens that you happen to not come in contact with, but you could see that were in your line of sight. And it made me think about augmented reality. We're always adding things to the world. When we talk about augmented reality, we're annotating it, but the idea is to enrich the experience. Could you foresee a time where augmented reality would be used to enrich the user experience by removing things from the world, by filtering the world for us and sort of making it less cluttered?
Yeah, that's definitely an interesting application. I think some early examples of that type of technology, obviously I'm very biased toward driving use cases, but if you imagine actually what backup cameras, which are now quite ubiquitous in the United States, what they're doing is, maybe we don't think about this all the time, but it's actually showing you a lot of things that even if you were turned around and looking closely, you wouldn't be able to see, because the camera is located somewhere that's blocked by either the rear seats in the vehicle or the trunk. And having a camera that's often like kind of near where the license plate is actually gives you a full, unoccluded view of the back of the vehicle. Another similar application of this would be thinking about the blind spots that are created. If you are making a lane change and you look over your left or your right shoulder, you have to think about, okay, if the vehicle is full of stuff or people, or even if it's empty, you have to think about the A pillar and the B pillar. So that's when I say A pillar and B pillar, that's structural vehicle frame between where like the driver is and where the backseat passengers are. That's where the B pillar is. The A pillar is over in front, connecting the windshield to the side windows. So you can use augmented reality in this case if you have a camera there with an unoccluded view of the blind spot area, can actually show the driver all of that frame without the A pillars in the way if you have a camera located just outside the vehicle. And I think Tesla, for example, I think is also experimenting with ways of using cameras to replace mirrors, which gives you a lot of freedom in how you can reduce blind spots that would be naturally occurring if you're constrained to looking at a true mirror from inside of the vehicle.
Okay, so in these examples, when we talk about removing things from the world, what we'll be talking about is removing objects. So removing these A and B pillars from the world and allowing us to look all the way through them, or removing, effectively parts of the car and letting us see all the way through so we can better sort of navigate the world. Is that the right way of understanding that?
Exactly. And I think one of the earliest applications of this, again, if you look at like advanced technologies that might be used by like a fighter pilot, if you imagine yourself sitting in the cockpit of like an F-22 and the pilot needs to know, like, is there another plane or another object I need to see that's directly below me? Fighter jets don't have rear view mirrors. And if you want to know what's directly beneath you without doing a barrel roll, they actually have really advanced helmets and other sensors on the plane that allow them to see what's directly beneath them. So a lot of these same innovations also have corollaries that can apply to driving scenarios.
All of this sounds really amazing, and every time I hear someone like you that has a really deep understanding of those talk about it, I think, wow, there's so many possibilities out there. But like every sort of technology, I mean, they're all facing adoption problems, essentially. There's never going to be 100% adoption of these technologies. But if you think about some of the things that are sort of blocking AR or standing in the way of a much greater adoption of it, do you think about the technical problems that need to be solved, or do you think about cultural issues that we need to sort of clarify for people around the technology? Which one sort of represents almost like the biggest threat to AR?
Sure. I don't know if I would see it as a threat, but I'd see it maybe as a barrier to adoption. But I think the number one thing is probably the hardware problem. And it has to do, specifically for driving, the hardware problem has to do with how difficult it is to implement a heads-up display or a HUD. But if we even think about consumer like wearables, I think that's an area where a lot of progress is being made right now. But a lot of the advantages and like really fun immersive experiences today, if you think about like what you can do with like an Oculus, where you put something on, that's actually that's VR instead of AR. So you're inside of a virtual environment that is able to track your head movement and everything. But what I think makes AR a really killer application is when it becomes an experience that is not using a screen, but actually directly augments your vision. So it's something that you can wear on your face. So imagine like Google Glass or something similar like that, and being able to connect a real-time understanding of what someone is looking at with the physical world around them, and then drawing objects into that environment. And there's a lot of like really powerful experiences that you can build on top of that if a user no longer has to hold something, but actually has free use of their limbs. So if you imagine like a lot of Oculus experiences that I've played around with, like I'm imagining the game like Beat Saber, where you're wearing something on your head, but you actually are holding two sabers in your hands that are also allowing you to interact with that environment. And that's not something that's possible if you have to hold up a phone and point it at something. Very similarly, if you're a driver driving in a vehicle today and you don't have a heads-up display, then you have to have a screen that you look at to actually see the AR experience that is not looking out the windshield while you're driving. And obviously that creates some safety concerns. So a lot of the shortcuts to make this work today have to do with putting that screen as close as possible to the real world, or designing it to only be used in certain situations. So that would be like the backup camera, for example. You're not supposed to look at your backup camera while you're driving forward, which is why the rear camera in most vehicles only turns on and shows the screen when the driver is actually backing up. And since you're actually able to see much better looking at that screen than actually looking at the back, that's a pure safety play. But in driving applications, we really have to think about safety because that's always job number one in a dangerous thing like driving. But I think for either case, putting the AR experience in a way that it's very natural for the driver or for the user, and they can use their hands for something else. I think that is what we're really waiting on. That is mostly a hardware and systems challenge.
I think that the Google Glass experiment was really interesting, right? Like, I'm not quite sure how well they did it in terms of the technology, but the adoption of having something on your face, that seemed to be like a cultural problem more than a technological problem, at least in my humble opinion. And it'll be interesting to see what sort of solutions win through. Like, I can definitely see the heads-up display when you're talking about driving a car, but moving around the real world, I can see we're going to come back to that cultural issue of, like, do we want to wear something on our face? Like, how can convincing the public that this is, worth doing, if you understand what I mean?
Yeah, that's so thinking about the consumer space. So actually having AR experiences that are like games for individuals as opposed to constrained to the vehicle environment is something where I don't have quite as many insights, but I do think that is a space where since culture is going to define your demand and the types of games and experiences that people are interested in, I think that's an area where it's much more important. Whereas I think in a vehicle, anyone who's experienced a prototype of augmented reality navigation that's implemented with a heads-up display is going to love it because it basically gives you the same kind of overlays and information you would get in a video game and like add all that extra context and allow you to keep your eyes on the road. So like a really concrete example of that is a lot of the earliest heads-up displays, all they're doing is just showing the speed limit in the windshield. So you don't have to look down at the speedometer. And maximizing eyes on the road time for drivers is very healthy. So I think that's a pretty clear-cut advantage. If we're talking about the gaming space and wearables as something that are used all the time, I think the cultural pushback might be from sort of an elitism of like only few people being able to afford or have access to the technology, which I think was the case with like Google Glass. But I think as these things become more democratized, more affordable, and as ubiquitous as like smartphones are now, I think if you also think back to 10 or 15 years ago when like iPhones and Android devices first started being something that everyone had, I think there was a sort of a similar like, oh wow, that's kind of snobbish that this person has like the very first iPhone and like can browse the internet in their pocket, and now we just take it for granted. I think there's going to be a very similar type of gradual adoption and initially some discomfort that will be overcome if the real value of that is able to be demonstrated and experienced by the broader public.
Yeah, I agree with a ton of what you said there. It makes a lot of sense. I want to sort of jump back in the conversation just a little bit now. So this is a geospatial podcast. We're all about geospatial stuff. And it seems to me that sometimes we need this really detailed map of the environment, which involves a lot of, geospatial stuff, a lot of mapping, a lot of rendering, a lot of processing of data needs to happen in order and on an ongoing basis as well, because the environment changes. But then we've got this other side of it where, depending on the application, all we really need is that point in space, that 3D point in space, and then we calculate the camera view from there. Could you imagine a time where this isn't a really heavy sort of geospatial problem, where we don't need that background map? Because I'm thinking of the way humans navigate. We walk around the city, and even if we have never been there before, we understand that this is a building, that it's a three-dimensional object, and things can be seen from one side and not the other side. Could you imagine getting to that place where, in terms of AR, we just need a really, really precise location for the camera?
I think it depends on the application. So if you think about, there's a couple interesting things to unpack there. So first, if you think about driving today, if you're driving in a place where you're quite familiar with where you are, then most drivers today don't actually use navigation. Like, for example, if I'm just driving to work, I drive to work every day. So I don't even open navigation unless I need to know about something like traffic. So if we think about, like, which situations require a map and which don't. I think the map is most important if you're going somewhere you might not be super familiar with, or if there is a particular aspect of your trip where having some additional guidance could be helpful. And there's also a lot of really cool AI features built into many navigation applications today where they try to figure out what you're trying to do based on your past behavior. So for example, if you drive to your office building and then back from your office building to your home 5 days a week and you've been doing that for months, then this is something I just noticed, like this is 4 or 5 years ago. I would notice like when I sat in my car, my phone would give me a push notification. It's like your estimated commute time is 45 minutes. Like I didn't have to tell it that. So because a lot of our devices today can learn about what we're doing to try to make suggestions based on context, I think those same situations could be used. Like if you get close to your destination and you need to find a place to park, like one example of AR would be telling you as you get close to your location, it's no longer telling you like what turns to make, but it's telling you like, oh, these are all parking spaces. This is how much they cost per hour. This parking space is handicap only. And you can make that information much more easy to access and see for a driver than if the driver had to slow down, hop out of the vehicle, like read the meter and things like that. In terms of like whether we really need a map or not for these sorts of things, there's a ton of really like low-hanging fruit type applications that do not require any more detail on a map than we already have. So like, for example, if I think about a lot of the applications that we've been working on at Mapbox in this space, we're using the exact same road network to drive our AR application as we are to drive a traditional two-dimensional navigation application.
That's really interesting. I really had this stuck in my mind that we were going to need these incredibly complex maps in order for this to work. They were going to need to be updated on a regular basis, available all the time and constantly downloading to our phone, to our car, to whatever. I think that's really incredible that, it can work today with what we already have. No updates needed.
That definitely applies to a lot of cases. There are some exceptions to this if you think about some other products that are on the market. So there's one that Google developed, I think about a year ago, for walking directions, where if you are walking around pretty much anywhere in the world, you can get walking directions that appear in AR. So if you just like point your phone ahead of you as you're walking, it'll figure out where you are and actually highlight a walking path to take. In this case, the way they actually implemented it is something that most companies wouldn't be able to do because they are doing image matching, picture matching from what the phone is currently seeing against their base of street view imagery. So in that case, they're actually solving the pose problem of what is the location and orientation of the camera by comparing the real-time imagery that you're looking at with the stored historical imagery they have from their street view project.
Wow.
And that's a case where having a just titanic amount of data on the server side to compare to your real-time observations can give you a very precise location, even if GPS isn't very good. However, this is not something that would necessarily scale well to all use cases, because if you think about vehicles, you're driving much more quickly, so the environment around you is changing quite quickly, and you also have to consider the bandwidth that is used there to compare real-time video with cloud imagery is quite expensive. And then finally, the level of precision that you're able to get in a vehicle as you're driving through a city is actually, it's not just reading your GPS, it's also doing something called map matching, where it is looking at your past couple seconds of GPS fixes, or maybe even the past like 20 or 30 seconds, and then doing dead reckoning using the IMU on your device, and then trying to snap, so to speak, snap each of those GPS fixes onto the road network and make some assumptions about, okay, this is the way a car would have to travel through here. And the reason Google did this very differently for walking directions is because if you are walking around a park, you don't have to follow the rules of a car. So you can change directions very quickly, you can turn the phone very quickly, you don't have to walk on a path, you can walk off the path. So because of all those assumptions that are violated if you're just a pedestrian, the approach of looking at street view imagery actually makes a lot more sense. But if we think about driving, even though driving has some different challenges, there's also a lot of assumptions we can make to constrain the problem of solving that pose to build sort of generalized understanding of how a vehicle would be moving through the road network and how that vehicle might want to interact with different objects in that road network.
Tori, I really want to thank you for taking the time to walk us through all this. I mean, you are clearly an expert in your field. It's often a little bit intimidating talking to people like you because I feel like every question is a dumb one. But I think you've done an amazing job of being patient with me, again, of walking me through the process of explaining things, and it's greatly appreciated. So thank you very much for your time. If the listeners want to reach out to you, if they want to learn more about the work that you're doing at Mapbox, is there any resources you could share with them? Is there any places they could go to connect with you?
Yeah, absolutely. So if you want to see some of the stuff that we've been building, you can actually just go to mapbox.com/vision. You can also follow me on Twitter. I'm just at Tory Paul Smith, ToryPaulSmith.
Excellent. Thank you so much for your time. Much appreciated.
Cool. Thank you.
So I really hope you enjoyed that interview with Tori. Again, I think a lot of really interesting stuff there. A few things that really stuck out for me was firstly was this idea of local and global. So local augmented reality, I think perhaps a really good example of this is the filters that we're used to seeing on social media, where I have rabbit ears that appear on my head. So this is not augmented reality in a global context, is local to everything that's happening onto the screen. It just has to identify my head and then put the rabbit ears, the bunny ears on top of that object. And then of course there's the global augmented reality. So this is in a global context where we want features to interact with reality, with what's happening in the real world. And this is a lot of what Tori focuses on. He focuses on the navigation aspect of augmented reality in terms of driving. And I think this is absolutely fascinating, the idea that digital features, digital objects can interact with reality in a global context. Several times during the conversation, you heard Tori talk about an experience, so a digital or a augmented reality experience, and building these experiences for people. And oftentimes when we talk about an experience, we talk about something that's personal, something that's really relevant and relative to you. And this is the same thing we experience on our digital travels in the internet. So the way I experience the internet is very different from the way you experience the internet. The way I experience the internet is based on my search history, all the other data that Google knows about me, my location, my age, these kinds of things. And I look at the internet as something that folds itself around me, that personalizes itself and adjusts itself to me as I move through it based on these things that Google knows. I wonder what'll happen when we travel around in these filter bubbles, not just in the internet, in our digital lives, but also when we take it out of the digital world and overlay it over the physical world. I wonder if this personalization of physical space and personalizing experiences, I wonder what that's going to mean for our shared understandings of locations, if that common sort of understanding of place is going to be further diluted. So I really hope you don't mind me sharing my thoughts with you here at the end of some of these episodes. I do this on purpose at the end with the hope that if this is something you're not interested in, you can just skip the end bit and still get all the benefit of listening to the actual podcast part. For those of you that have made it all the way to the end, I want to thank you so much for taking the time to listen. I realize there is a lot of other options out there. There's a lot of competition for your attention, and I really appreciate you taking the time to listen to this podcast. That's it from me. I'll be back again next week with another episode, so feel free to tune in then. In the meantime, you're more than welcome to reach out to me on social media. Just search for Daniel Mapscaping Podcast, something like that. You'll find me. I'm most active on Twitter and LinkedIn. You can also check out our website, mapscaping.com. There's email addresses there if you would prefer to contact me that way. I would really love to hear from you. Thoughts, suggestions, ideas are more than welcome. Okay, we'll talk again next week. Bye.